Hello friends, welcome back to the Dr. Tristos channel. I'm your host, Dr. Tristos, and I wanted to continue our sample program today, and maybe we could expand on it a little bit and from the last video for the Easy 80 programming, and I thought we would stick with the same sample we started with before and modify it. So let's jump into it here. I changed some labels here. I got example demo, as we're going to call this program, example demo. In the very first instruction we covered before, we're originating the code at 3000 hex. You should be able to see on your screen here the org statement. So the code orgs at 3000 hex, which is a standard Tristos starting location for applications. So we can use that standard address. Makes it simpler when we actually write an application for Tristos, so we'll already be used to using it. So example demo begins at 3000 hex, and the first instruction is a jump to begin app. So that's changed a little bit from where we were at before, and because we've added data. We've added data that we're going to output out the UART, and so that'll be kind of the purpose of this code modification, is that we're going to exercise and use the UART, which we're lucky in that it will output out the simulated UART that's in the development system software that's free from Zilog.com. So we have this data that immediately follows our example demo jump to begin statement here in the beginning. We immediately have data. I called it data string, and this statement here, db define bytes. Many different ways assemblers handle these. The way the Zilog development system, when you have a constant, a set of constant bytes after the statement. These could be numerical, or in this case we're saying ASCII. So inside the double quote it says hello world exclamation point, and that's inside quotations, double quotes. So that tells the assembler at this label in memory to place this string in ASCII. And then we have our first label, begin app. If we remember, we were jumping directly to here, and we begin. We begin with a no operation. It's like Monday morning at the office. Nothing's going to happen at all when this instruction executes, other than it will burn up a few nanoseconds, and I just like it being there. First thing we're going to do is load the H&L register pair with the address of data. Remember, data was here, the label for data, and this label points to, or is at, the ASCII string hello world. So we load the address of data into the H&L register pair. We don't want to, before in our example program here, we loaded B with 0 because we just looped and did nothing for 256 times. We added some numbers and moved some data in register, and we looped 256 times. So we loaded B with 0 because 0 causes the maximum number of loops. And but this time, everyone knows that hello world with an exclamation point is 12 bytes long, so we're going to load our B, our counter, with 12. So now it's time to output our first, or get ready, check and see if we can, test ready is the label here, test ready. We're going to see if we can send, if the UART is ready to receive. And the way we do this is by testing the transmitter holding register. The transmitter holding register is holding what needs to be transmitted, is waiting to go out the door of the UART. The UART is doing its job. Maybe you're feeding it bytes. It has one in flight. What I mean in flight is the UART has started serializing and transmitting a byte, and you come along and say, I want you to send another one. Well, really in the very old days, you couldn't do that. You had to wait till the old one went out. But most today have some sort of buffering of at least 1 byte, a holding register. And here, when it's empty, the holding register for the next one that'll go in flight, when it's empty and whatever was in it is sent in flight, or maybe nothing was ever sent, it will be empty. So we need to get the contents of that register, which is register Charlie 5. This is hexadecimal. Since it's hexadecimal, I have to start it with 0, because if you didn't, the assembler wouldn't know if you meant a label Charlie 5 H. C5H. They wouldn't know if you meant a label or a hexadecimal number. So we start with 0. The assembler says it must be a number coming of octal, binary, decimal, something. You send it a Charlie 5 with a hex H tagged on. It tells it's a hexadecimal number. So we're going to input from this port Charlie 5. Now, how do I know I want to input from Charlie 5? Well, let's go to our product specification manual, the EZ80F91 specification manual, page 192, which is the UARTs. And we're looking at UART0, because that's the one we're dealing with here. And we can see here is bit 5. If the value is 0, the transmit holding register is not empty. So if it's a 0, it's not ready because it's not empty. There's something in there waiting to go in flight. If it is 0, we must wait or do something else. If it's a 1, on the other hand, if it's a 1, it's good to go. The buffer is empty and it's ready to receive another byte to send. And that's an 8-bit byte of ASCII or extended ASCII or data, whatever you're sending. Note that Zilog uses abbreviations for these bits, and this one it calls THRE. THRE, transmitter holding register empty. That's what that stands for. Transmitter holding register empty. And this becomes important later because we want to start giving names to these registers. It makes things more readable. So, did I show you the address in the manual of this? Is at UART0, the line status register, right here, table 106, for the address is Charlie 5 for that register. And for UART1, the bit pattern is the same, the register works the same, it's just the address is Delta 5. And you'll find that that's how they're separated on most of the registers, where you have two different ones, two UARTs or multiple timers or something, they're spaced evenly. So we can see here that all of these bits, if we look at this table on reset, this gives you the value they will be set to on reset. When you do a hardware reset, bit 7 will be a 0, 6, 5, 4, 3, etc. will be zeros. 6 and 5 will be set to 1. How can you access these? The only thing you can do is read these. You cannot write to these bits. They're read only. So since we're doing very simple UART communications in this example, and we're not trying to do handshaking or other complicated UART control codes, etc., we only have to worry about if it's ready to receive another character, to send a character, and then to give it a character to send. So let's go back to our code here. We're going to test that bit, and we've already said that if it's a 0, it's not ready. So we're going to jump relative. If that bit was a 0 after we did the bit test here, bit 5. Remember, it was bit 5 that showed the status. If it was a 0, it is not ready, and we're going to continue looping and input it again. Test the bit again, and then decide if it's ready or not. When it is ready, you fall through, and we're going to load the accumulator with the contents of the H&L register pair. What is pointed to by the H&L register pair? That's important, that we're not loading the contents of H, L, or any register into A. We're loading what is pointed to in memory by H and L. Well, if we remember above, we loaded H and L with the address of data that contains hello world. So the first time through the loop, H and L is pointing to the first letter, H. So we're going to pick that up. We'll pick that letter up, and then we're going to output that. Output register A to address Charlie 0. I say we, out the port we go. Yes, out it goes. Let's see. How do I know I want Charlie 0? Well, again, let's look at our manual. And have to... There's a lot of registers in this, but you don't need all of the different registers to write simple programs. I mean, it's capable of doing many different protocols, many different things, but you don't necessarily have to program all that. That's the point of this video, is to show you how simple this is. So this is the transmitter holding register that I was talking about. It's holding what's going to go into flight. And UART0 THR is the abbreviation for this register, transmitter holding register. That address was Charlie 0. If we look on reset, all bits X means we don't care or we don't know what they will be. They're undefined. Doesn't matter. How can we access this register? There's only one thing we can do, is write to this register what we want to be transmitted, which is exactly transmit data byte. So going back to our code here, A contains the first character, H. We're going to send that. We know that the UART is ready because we already tested up here and it became ready. And we now output. With this out instruction, we send that character out, the UART. We're now going to increment the H&L register pair. H&L will be a 16-bit register pair. It's pointing to a place in memory where our data is contained. It started out pointing to H. We now increment it, and it's going to point to E. Remember our counter? We told it 12 characters right here. Load B with 12. That set us up for 12 characters. So we're decrementing and jumping if it's non-zero, register B, and we decrement register B. We're starting off at 12. If it's non-zero after we subtract 1, we have that here in the notes, what's happening. Then we loop back around. We're going to go back to test ready and see if it's ready to accept another byte. If that was the end, it was at 1. The last time we went around the loop, we had just sent the first character. It comes back around here. We're on 1. This is going to be a 0, so it's going to fall through the loop, and it'll come here and halt. Again, I use halt in the simulator, running the code here in the simulator. If you're doing a development system and it's running on a board, I recommend you just use an endless loop or something, because when you execute a halt, you lose control of accessing the CPU through the debug facility and being able to read the registers and everything. So, or at least it does for me. I've never figured out a way around it. So I'll tell you what, let's see if this will run. And we're going to do that first. We're going to build it, build all. We only have one module, so building all means build this one module. And if I look down here in my output pane, it successfully built. Base address is 3000. Top address, I think it's the highest it used in the assembly. 0 warnings, 0 errors. So now if I click this down arrow, if we were using a development system, this is where we would download the code and go on a development system, load it into the development system's RAM and tell the CPU to begin at location 0 or whatever we have set up. But in this case, it's going to run in a simulator, so I'll press go, and it assembles and builds, and it's already ran. Here's the output of UART0, hello world. So this program output this code. If I break our project, we will see that we're down here. Here's our disassembly of what's been executing. The yellow arrow says we're setting at this halt instruction. And if you look at the program to the left, you'll see it's a disassembly. It simply has the addresses, the absolute physical addresses added to it. And yeah, so our program's looking really nice. But sometimes as assembly language programmers, we would like for it to be neater. So these are the things we've learned here so far. And we have this, and I told you that, well, we can add blank lines. Most assemblers I've dealt with require a semicolon on the line to let them know it's a comment line. One thing I like about this development system is you can just have blank lines of carriage returns. And that makes our code more readable. You know, in C and Python and things like that, we use indentation to show the different levels of the code, and it helps the programmer understand what's going on and define what they want the compiler to do. Well, here we can use blank lines. It's not going to change the code, but we can make it more readable. Is one feature I like. And so I can kind of break this into segments. We have our beginning code up there, and then we have a data section. Okay, we'll kind of separate those by blanks. Then we have some code that gets us started up. We load up the pointer to the data, and then we load up the pointer to or the counter of 12 characters, ASCII characters. So now that we've kind of done that, we're in a loop where we're going to work with our data. So we start another new section here. And you can do this in any assembler. You may just have to add the semicolon to on the blank line. But like I said, I like the way Zilog did this. So look, we have a section here that does a test, right? And then after we do a test, getting the data and sending it out might kind of be a different section, and then certainly halting. And ending the program would all be kind of different sections. To me, this is all a whole lot more readable now. And one thing I told you yesterday was at the end statement we needed a transfer address on the load. And all assemblers I've ever worked with, that's true. I'm played with this offline today and was unable to get it to do what I had told you yesterday. So you can actually take this out. It seems to have no effect at this point. We'll play with that further in the future. Wherever we org at here is where the assembler is starting the code. So I need to play with that in the future to know if it's true. Most assemblers I've worked with requires at the end statement we have the transfer address, unless you're just writing a module that's called and loaded in memory by a routine that's controlling it. So anyway, we'll have to delve further into that. So I'm going to cut this video off here. This should, we have a little better readable program. Maybe the next time we'll make this a little more readable and expand it a little further. Maybe let's add and make it do some additional steps here, and keep building, and maybe we can build a little sample program to do something that's kind of useful, even though we're running through a simulator. Okay, so thanks very much for watching. Many thanks, and I hope to see you back here again. Bye-bye.